In this lecture, we're going to look specifically at water. So water has a lot of really interesting properties that are different. So we'll have two essential questions and that make it different and kind of our whole reason. Like you can live, I heard this on Human Planet the other day. What was it? You can live a couple of weeks without food, but you can only live a couple of days without water, like 2 days max without water. So essential question here is, what about the chemistry of water? Makes it so essential to life. Our second essential question, so I guess that should be 1, and this one's 2, is very simple. What is pH? So we're going to look at all of the cool properties of water, and it should boil down to just a few things, but we're going to look about what exactly about the chemistry of water makes it so essential. What is it that makes it be able to support life so well? And then what is pH? So water has a few properties that are pretty unique. Well, not unique, it's just the fact that it has all of these properties that make it so unique. So some of those things is it has a tendency to stick to different molecules. So it has a tendency to stick to different molecules, but also stick to itself. So when we call it sticking together or stick to self, I could say stick to self, we have the term cohesion. Okay, and so it's cohesive. It works kind of together. It sticks to itself. So cohesion is much stronger for water than any other liquids. And you know that it's cohesive and it's sticking together because if you have a little droplet of water, it does like this. It's because it's all sticking to the inside and trying very hard to stick to each other. That's what's so interesting. Most plants actually depend on that cohesion in order for water to be transported up the roots. So for water to defy gravity, if you will, to go from the roots all the way to the top to the shoots, then you need some extra properties, and it's cohesion that does that. The other thing is that it has a tendency to stick to other things. So two kinds of molecules stick together, but basically it's just stick to other stuff. And we'll look at lots of good examples of this, but if you take water and you kind of touch it and then it kind of sticks to your finger for a second, that's adhesion. And it's a different thing. Alright, cohesion is related to surface tension. So surface tension is how difficult it is to break the surface of a liquid. Some things are fairly easy, but when it comes to water, it's actually difficult to break the surface tension. There's lots of things that utilize that. So hydrogen bonds, what we talked about a bit in the last lecture, those hydrogen bonds give water a really high surface tension, and they make it behave as if it were coated with an invisible film. We'll look at some cool videos about this kind of next class. Water striders, and these are some cool guys. They bite like crazy. They're mean, but they're really, really cool because they actually use the surface tension and have kind of adapted legs that can stand on the water without ever going through it, and they can skip on it. We'll look at videos of those too if we haven't already. Until I'm making this ahead of time. Okay, so this is one of those examples. This is an animation that we'll look at for sure a little bit later, but you can actually see water molecules sticking to themselves to get up, but then also sticking to the walls. So they stick together and pull each other up, but then also stick to the walls and kind of get their grip that way. Alright, so there's a water strider sitting on top of the water. That's pretty much exactly what they do, and they scoot, scoot, scoot. Okay, so thermal energy, I have a really great video for this. It is so cheesy and lame, but it works really well. So thermal energy, thermos, think like thermometer, think of all those things. It just means it's related to heat. So thermal energy is kind of a heat energy, associated with the random movement of atoms and molecules. That's actually heat. The more randomly they move, the faster they move, the more heat is usually associated with them. So thermal energy is a transfer from warmer to cooler body of matter, and that's defined as heat. Temperature measures the intensity of heat, that is the average speed of molecules in that body of matter. So in a solid, they're still. There is no movement, so we know it's a solid. There's usually not heat associated with that. But if I get to a liquid, thinking like water, a liquid, I heat it up, those molecules will start moving a little bit more. That's why it's fluid. By the time you heat it up a little more and it's a gas, it's like, forget about it. They're all over the place. Okay. So heat must be absorbed to break the hydrogen bonds. That's what we're getting at. All right, so heat has to be absorbed to break hydrogen bonds. That's a key point there. When heat's released, hydrogen bonds form. So the more hydrogen bonds we have, the less movement of the water. So to raise the temperature of water, hydrogen bonds between the molecules have to be broken before they can move faster. So when warming up, water absorbs a large amount of heat, and when water cools, water molecules slow down, more hydrogen bonds form, and a considerable amount of heat is released. Do we have a picture of that? No, I don't. But I'm going to come back to this as a point. I thought I had a picture of it. But we'll really take a look and examine the hydrogen bonds in each of the states of matter of water. Okay. Earth has a giant water supply that helps to moderate temperatures, and that just helps keep the temperatures within limits that permit life. So it really helps to regulate temperature. You might notice that a little bit more like coastal regions, so even here, as hot as it is, our temperatures stay relatively the same. If you go into a desert, you can experience well into the hundreds during the day, and these are more inland usually, and then well below zero at night. And so there's just this huge fluctuation, but where in the coastal regions, ours stay relatively the same. There's not a huge difference. Water's resistance to temperature change, which is, there you go, resistant to temperature change, also stabilizes those ocean temperatures and creates a favorable environment for marine life. So it doesn't get too crazy for the things that live in the water as well. This one's actually good for us, evaporative cooling. That's like when we sweat. So the surface of the liquid remains behind, cools down. Did we get that? So when a substance evaporates, the surface of the liquid that remains behind is cooled down, and that's evaporative cooling. So this cooling occurs because molecules with the greatest energy will leave, and so they kind of take the heat with them when they evaporate. So that's actually how we sweat, and that's actually how we cool down when we're hot, which is a really, really efficient thing if you're from Houston, right? Or the Houston area anyway. So water can exist as a gas, a liquid, and a solid, and this is at kind of naturally at any of these states. Like we have liquid nitrogen, but that nitrogen's normally a gas. To get it to liquid nitrogen isn't actually natural or realistic, but it's just what we do. But naturally water occurs in all three, and this is one of the things that makes water unique. Okay. Water, interestingly enough, is less dense as a solid than it is as a liquid, and you knew this. You didn't know that you knew it, but think about whenever you serve yourself a glass of water. I'm going to make it terrible. Here's just some little ice cubes, and notice they float, right? I know, it's a terrible drawing, but you get the idea is that the ice cubes float, so obviously they're less dense than the liquid water. Same thing, it's just that one floats. That's also another unique property of water. There's not a lot of other things that become a solid and float in themselves. Really weird. Okay. When water freezes, each molecule forms a stable hydrogen bond with its neighbors. So that's what it does. This one will have a picture. So as the ice crystals form, the molecules are less densely packed. They actually spread out. And you know that too, because if you're like me, you've done some you've put like water in a bottle and then you put it in the freezer and you've overfilled the water bottle and then it splits a little bit. So water expands as it freezes because it's going to pack out a little bit differently. It's going to spread out as it packs, or as it packs and freezes. So that's why it's less dense, that's why it floats. So if you notice, this is liquid water. It's hydrogen bonds are forming this way. And they're kind of, they move around a little bit. So this one will disconnect and it'll form a hydrogen bond here. And then that'll disconnect and it'll form one here. It's kind of it's a fluid, so it's a fluid process. It's like it's handshaking with its neighbors. But when it's frozen, it's like it's in handshake with its neighbor and time stopped. And so that's as far out as they're going to be. They're not going to mingle or get any closer like they might down here. They're just spread out and they're frozen, and kind of time is frozen for them. So they form this nice structure, which is actually, you see, a lot more spread out, which is why it's less dense and it floats on the liquid version of itself. What a weird thing water is. All right, we're at the 11-minute mark and we're going to start solutions. I think this is an excellent time to remind you to take a break. Pause your teacher, go do some things, and then come back. All right. By the way, since we just, either you braked or you didn't, it reminds me, there's something I like to do occasionally, and I call them Easter eggs because, DVDs sometimes had Easter eggs in them, and that's what they were called, and you could find special little things. So I call these the Easter eggs because if you're listening, you'll get bonus points. So I learned the other day that the captions on these videos are not always accurate, or I guess, sadly, maybe not appropriate sometimes, which bums me out. But here's your bonus point, and usually it's content related, but today your bonus point, which will be for your quiz, you got to make sure that you bring this next time for your quiz. Got to bring it. If you give this to me, I'll give you 1 point, which is about 5. It's equal to 5 points on your quiz. If you bring me, you got to timestamp it for me, but you got to say not what I was saying, but whatever was interpreted, and then give me the timestamp. If it's not school appropriate, put not school appropriate and give me a time, because I got to know what's coming up on the bottom of this thing. So if you can tell me what kind of caption comes up that's clearly not what I'm saying and give me a time on it, I'll give you 5 extra percentage points on your quiz. So there you go. Took me a minute to say that. I apologize, but you know what? Bonus points are worth it, right? Okay, now we're on to solution. So a solution, hopefully this should be a good review from chemistry also, as you should know a solution is nice and uniform, and it's a mixture of 2 or more substances. Hopefully you know that. The dissolving agent is the solvent. So it's usually in the greater amount. I think greater number of letters, it's the greater amount of things, and water tends to be the solvent. It's usually water. We're not, in this case, we're going to look at water, so that makes sense. The substance that's being dissolved, usually in the smaller amount, is the solute. When it's in water, it gets a special name where it's called an aqueous solution, and it just means it includes water. Well, it shouldn't be too hard. If you've taken some Spanish, water is usually agua, agua, and aqua, we know that as well, but either way, both of those work for it. Aqueous solution, it deals with water. So water's versatility as a solvent results from the polarity of its molecules. So polarity meaning that it has different poles and that it has some charges. So that's another way to think about it, is it has charges. So polar or charged solutes will dissolve in water, and the molecules surround them because water is a friendly little molecule and it just likes to make friends, and that's what it does. So an example of what does this is table salt. That's sodium chloride we talked about. So here's sodium chloride at its finest, and what happens is those individual ions will split, and as the chlorine has the minus sign, all of the little positive hydrogen ions, the hydrogen atoms in the water molecule will try to line up around that chlorine and kind of hug it. It's like just a total welcoming committee. Like, oh my God, you're negative, we're all positive. Let's come with us, it's going to be great. So it's just a beautiful little welcoming committee. At the same time, that nice positive sodium will come in and those negative oxygens will surround it. And I don't know if it's grumpier or not, but it's still a welcoming committee. And they're attracted to one another, and so it just readily dissolves this table salt down here. Easy, easy. So in liquid water, a small percentage of water molecules break apart into ions. Some are called the hydrogen ions, and then we have hydroxide ions, OH minus. And both types are really reactive. They don't necessarily like to be alone. So a substance that donates hydrogen ions to a solution is called an acid. Do we have an example? I'll give you one. So hydrochloric acid would be one because the hydrogen likes to react with a negative chlorine, not in the previous solution, but these guys kind of tend to react together because they just fit. And so these donated hydrogen ions will go with the chlorine and make it hydrochloric acid. Believe you me, this does not happen with that table salt scenario. It just doesn't, but that would be a different solution. A base is a substance that reduces the hydrogen ion concentration of the solution. So it usually has more of the OH in it. Okay. So sodium hydroxide, we can really use those. So sodium hydroxide is one as well. The pH scale describes how acidic or basic a solution is. So the pH scale ranges from 0 to 14. I hope this is a review. 0 is the most acidic. That starts to get towards like hydrochloric acid or battery acid kind of levels. They're getting strong. 14 is the most basic, and that's closer to something like lye or sodium hydroxide. Each pH unit represents a tenfold change in the H+ concentration. Okay? Hopefully we've learned that somewhere along the way. I'm moving on because I assume that some of this basic chemistry stuff is a review for you. If it is not, you just come see me. Quick, easy fix. We will discuss it in more detail. So a buffer, if you've heard of, maybe you've heard of a buffer, maybe you haven't, it's a substance that minimizes the changes in pH. So it can accept H+ or hydrogen ions when it's in excess, but it can also donate hydrogen ions when they're depleted. So a buffer is just helping make sure that everything stays in a normal range. It's hard to kind of give you better examples than that one. Just know that a buffer will do either role just to help make sure that things stay, as they are. Okay. Hopefully this is a good review for you guys. So remember, battery acid is way down here on the scale as far as like it's a 1 to 0 on the pH. It's really, really acidic, really reactive. Oven cleaner, which is similar to lye and things like that, is closer to 14. It's a very, very strong base. Pure water is right there in the middle. That's your neutral. So those things, the H+, the OH- concentrations, the brackets, by the way, mean concentrations, because nobody likes to write out concentrations. Seriously, scientists shorthand everything. Side note. But pure water is our neutral. And just so you know, which is kind of interesting here, is that human blood and tears are actually slightly basic. It's somewhere around 7.4 on the scale, and you actually naturally keep a basic kind of concentration or a basic pH within your body. I know, don't start with the basic jokes, alright? That's basic. Alright, scientific thinking. So scientists study the effects of rising CO2 on coral reefs because they actually have an impact on the pH level. And so carbon dioxide is a product of fossil fuel combustion, and it's increasing in the atmosphere. Those studies have been done on that. Okay, it is linked to global climate change, which is a better terminology for global warming. It just changes in the climate due to increasing CO2 concentrations in the atmosphere. All right. So 25% of the human-generated CO2 is absorbed by the vast oceans. So our oceans are really beginning to absorb a lot of the CO2. The problem with that is that it lowers the pH of the water, and it's called ocean acidification. Why? Because it's a process that's making the ocean more acidic. I mean, the name gives it away here. We don't have to look at this exactly, but basically this, we're just getting some issues. And so some of these concentrations have an effect and react with corals and other shell-building animals, because they tend to be kind of, I'm trying to give you an example. We'll look at it later, but it's like you can put an egg into vinegar, and the vinegar as an acid will break away the shell of an egg, and it's basically the same as this. So corals and shell-building animals kind of have this particular ion like an egg, and so as we make the salt water more acidic, it's like vinegar, which is an acid, and so we're getting this reaction where we're starting to reduce what's available for these guys, and it's really a bummer. So that's something to think about. Trying to think. I mean, you can read through this. You don't have to necessarily write it down. We could look at it. In a controlled experiments, scientists looked at the effect of those decreasing carbonate ions on those reef organisms, those things that kind of are like an egg. The lower concentration of carbonate ions, the lower rate of calcification, or building the kind of eggshells or the shells that they might have. And the results from the experiment showed that pH naturally varies. It has dire implication for the health of those coral reefs because they're kind of disintegrating a little bit. All right, so calcification rate. We just have more issues. I'm going to go into the chart right now. So rising CO2 bubbles will lower the pH of the water, thus making it more acidic. Okay, and then destroying the coral reefs or making it harder for them to rebuild themselves and repair. Emergent properties of water support life on Earth. And when astrobiologists search for signs of extraterrestrial life on other planets, they're usually looking for water. I can't remember exactly where, if they said, but they did say, NASA did say that they found some evidence that water might have been on Mars. And I say might because we like to leave a lot of room for error in science. It's hard until we build a time machine and then go back and say, oh, look, there's water on Mars. There's always a little room for error. Okay. But there is some evidence to suggest that. Alright, so we've finished up fairly early, which is better. I like to do that during the weekly videos. So, make sure that you're looking over your notes. Make sure that you after you finish, go chunk, write a few questions, little things on the side, write out your summary real quick while you're thinking about it. And if you have any questions, shoot me an email. But otherwise, we will discuss in next class.